Hello, everyone. This is Joseph Andrus, and alongside my colleagues at the University of Colorado Boulder, I work on quantum algorithms for dynamical modeling. Today, I'd specifically like to share our work modeling nonlinear systems using repeated measurements. Now, the real motivation for this work is that if we want to model a dynamical system on quantum hardware, and there are a number of reasons why we might want to do that, there's a distinct divide in what we can do for linear and nonlinear systems. For a linear system, we can leverage the inherent linearity of quantum mechanics and use that as the engine for our algorithms. The result of this work is the well-established approach of Hamiltonian simulation. For a nonlinear system, however, that is not an option. And so a lot of research is currently going into closing what remains an open question. Today, I'd like to go through our work on an approach akin to the classical forward Euler method, an approach which uses the linear method of Hamiltonian simulation just for short periods of time. Of course, to use Hamiltonian simulation, our system must be in a form friendly to quantum mechanics. And to achieve that, we have developed a method of mapping real polynomial systems, the summation form seen in equation 5, an equation with its central piece in the pairs of observables and Hamiltonians. This mapping is both physically realizable and norm preserving, which is important because those are our two requirements for quantum evolution. Now, to form an equation 5 relies on finding the expectation value of our series of observables, which must be done by repeatedly measuring each observable using many copies of our dynamical state. With infinite resources, we could find those expectation values exactly, but being limited to finite measurements, there will be some variance in the values we find. And thus, every time we run our algorithm, the simulated trajectory will be slightly different from the other times and from the classical result. Indeed, with enough measurements and short enough time steps, this approach converges first to the solution of a stochastic system and then to the classical model. To demonstrate this stochasticity, we turn to the Lorentz system, which is useful not only because it is a classic example of chaotic behavior, but also because we can eliminate that chaos by modifying our parameters. As a result, we can investigate the effects of chaos on the accuracy of our system. Now, the results of this algorithm are pictured in figures 1 and 2. On the right, we have the mean trajectory modeled, plotted against the classical result, while on the left, we have all the many trajectories simulated by our algorithm. For the well-behaved system in figure 1, we see that we maintain accuracy throughout, but for the chaotic system, there is divergence from the classical result corresponding to this branch in the trajectories. Now we can quantify how much of the trajectories have diverged and if they have branched by looking at the entropy of our ensemble of quantum states. And indeed, in figure 3, we see a corner in the entropy where the trajectories branch in figure 2. Now, if a low entropy is indeed necessary for accuracy, we would like to determine how this corner reacts to changes in our rate of measurement. How many resources do we have to invest in order to keep the trajectories together for our entire simulation? We investigate this question in figure 4, plotting how long the system takes to branch as a function of our measurement rate. In the well-behaved convergent system, there exists this asymptote beyond which the trajectories converge to a fixed point before they can ever branch, and thus the accuracy is maintained indefinitely. However, this does not occur for the chaotic regime. Looking forward, work remains to be done in quantifying the relationships seen in figure 4, as well as investigating further systems, especially systems of interest to plasma physics. Especially important to these may be the existence of well-behaved error-resistant statistics which remain accurate even if the underlying trajectories diverge. In the field of plasma physics, one of those trajectories, for example, could be the energy flux in a tokamak. I am so glad to have had the opportunity to share our results with you. Thank you all for your attention.